recording, and let's discuss now today's lecture topic. Last class session, we discussed oxymercuration as well as other reactions that proceed through a cyclic three-membered ring intermediate. In this case, we're looking now at reactions involving carbenes. Now, the main distinction for carbene formation is inherently both of the carbon-carbon bonds formed must be formed with a syn stereochemistry. And as a result, when we generate our three-membered cyclopropane, both of the bonds in our cyclopropane will be on the same face of our molecule. So for example, if we treat the following alkene with chloroform and sodium hydroxide, we know that these conditions result in the generation of the dichlorocarbene. Just to show that mechanism really quickly as a refresher. So sodium hydroxide abstracts a proton. Then chloride leaves, and that generates a dichlorocarbene. So the main feature of a carbene is it has an empty p orbital and a localized lone pair. The carbene overall is neutral, but it has an incomplete octet. They're pretty interesting species, and they can be utilized for a range of bond-forming reactions. In this case, when we have our alkene, so let's really pay attention to what's going on here. What type of alkene are we dealing with? Would we call this a Z or E alkene? Would we call this a Z or E alkene? Z. So this one drawn right here, this alkene is a Z alkene, right? Because both of our substituents are on the same side of our alkene. Now this is important because when we think about the stereochemical outcome for these reactions, there are only two different types of alkenes, right? A Z alkene and an E alkene. So if we know the stereochemical outcome for each of our two alkene geometries, we can essentially predict the stereochemical outcome for any alkene that reacts as long as it follows this mechanism. Okay, so we have our cyclopropane formation. We end up with our alkene attacking our carbene, and then our carbene attacking the electron deficient carbon on our alkene. Okay, this addition occurs with syn stereochemistry. So both of our carbene substituents end up on the same face. If you try to make a model, there's no way for you to have both of these bonds trans to each other. So this bond formation occurs to yield a product with syn stereochemical arrangement. Okay, so this is a complete summary for the stereochemical outcome for the following cyclopropanation reaction. Now this structure can also be drawn from a side-on perspective where we have our carbene on the top face. And then we have our hydrogens on the opposite face. Either way is fine. I personally prefer the dash wedge notation since it's more explicit. Does this make sense to everyone so far? So when you're using a carbene to generate a cyclopropane, it occurs with syn stereochemistry. Don't draw the cyclopropane substituents trans to each other. That's geometrically not allowed. Okay. So let's now look at an E alkene. So in this case, let's pay special attention here. We're going to make a model. So these conditions end up generating dichlorocarbene. Okay. And from these carbenes, we can subject them to a range of different reactions and generate more interesting functionalities. But for now, let's look at how this dichlorocarbene will react. And let's try to get a sense, let's try to understand a little bit the stereochemical outcome using our model kit. And this is the kind of thing that I want you to be doing on the exam. There's no reason to shortcut. Once you've practiced enough, you'll be able to visualize this process without the need of a model kit. But until then, I highly recommend just breaking out the model kit whenever you can. It'll save you a lot of time and energy. Okay, so let's get things set up here. Hilariously enough, this alkene is symmetrical. Not that that has any relevance in this case, but interesting to note. Okay, so let me get the video all set up. Whoops. Okay. Can everyone see the model kit? Can everyone see the model kit okay on the camera? Okay, so as we notice, we have our alkene all set up and ready to go. Now, we have our dichlorocarbene, and our dichlorocarbene can either attack from the top face or the bottom face. There's no preference. We don't have any auxiliaries, no stereochemical bias in this molecule. It's perfectly flat. Either face can be attacked. Arbitrarily, let's just draw the attack from the top face. So we're attacking from the top face. Does everyone see that? We're attacking from the top face. Okay, so this attack occurs with syn stereochemical outcome. Cyclopropanes are always a real pain to get set up. Okay, here we go. So we've attacked from the top face and we have the following cyclopropane. As you can tell from the way the model kit looks, cyclopropanes are pretty strained. Okay, so let's draw that attack. So we're arbitrarily going to choose to attack from the top face. So one arrow goes to the alkene, the other goes from the alkene to our carbene. Okay, perfect. And now let's just draw what we see. So in our cyclopropane, what substituents are pointing towards us? Let's start on the left. What's pointing towards us on the left? What group is pointing towards us on the left? The ethyl, exactly right. So we draw that with a wedge. And now what's in the back on the left? What's in the back on the left? The hydrogen, yep. Okay, now what's in the front on the right? What's in the front on the right? The hydrogen, yep. And what is in the back on the left? Sorry, what is in the back on the right? Sorry about that. What's in the back on the right? What's this group in the back called? The ethyl. So does everyone notice how if our substituents are trans, are on the opposite side of our alkene, they end up on the opposite side with completely opposite stereochemistries in the final product. Does everyone see that? So you also end up with the enantiomer. You also end up with the enantiomer, which looks something like this. So one shortcut that you could use in this case is just anything that is, so you can draw out your alkene. You can draw out your alkene. And then you can draw a dividing line. Anything on the bottom side of the dividing line will get a wedge. Anything on the top side of the dividing line gets a dash. That's one method of drawing the products for this cyclopropanation reaction. I don't personally like this shortcut, and I would prefer that you validate your product stereochemistries using a model kit. Okay, so we see we've generated the two following enantiomeric products. Does that make sense to everyone? Perfect. So let's keep going now. And let's talk about another reaction that can generate cyclopropanes through a carbene intermediate. This time we're adding an equivalent of a methylene group rather than a dichloro group. Dichlorocarbene, we're just adding a hydrogen substituted carbene. So reaction of diiodomethane with a zinc copper alloy produces a carbenoid species. So this can be functionally viewed as the following carbene. The zinc copper alloy is essentially activating one of our carbon iodine bonds, and in turn helps facilitate breaking one of our carbon iodine bonds. Okay, so once we have our carbene generated, the mechanism is identical to your typical carbene addition. So in this case, what kind of alkene are we dealing with, Z or E? Always keep that in mind. What type of alkene are we dealing with? Z, okay. So we generate our carbene this time. Because our starting material is diiodomethane, we have two hydrogens on our carbene rather than two chlorines. And as a result, this carbene, although it functions through the same general reaction mechanism, the final product, your final cyclopropane, will have slightly different electronic behavior. Okay, so we have our carbene addition, and in turn, we generate the following cyclopropane product. We also end up generating the enantiomer. And now, this is a really important question. Is this a genuine enantiomer? Is this a genuine enantiomer? No. So do we need to put this? Do we need to put this plus enantiomer? Is that entirely accurate? Do I need to put plus enantiomer in this case? Oh, whoops, sorry about that. Bad habit of mine, yeah. Perfect. So we don't need to mention this enantiomer because in this, if we look at this molecule, it's perfectly symmetrical. Any other questions on this example? Okay, so let's look now at another reaction that generates a three-membered ring product with syn stereochemical outcome. And this is a pretty important reaction. It's known as epoxidation. A lot of work has been done on enantioselective and stereoselective variants of these reactions. We're going to look at the normal epoxidation reaction first. So we treat our alkene with M-chloroperoxybenzoic acid, otherwise known as MCPBA. And in the end, we end up generating this three-membered ring containing oxygen known as an epoxide. The key feature of this reaction is that our epoxide addition occurs with syn stereochemistry. Yeah, so when you talk about the phrase epoxies, they're derived, or polymeric species derived from polymerization of epoxides. Yeah. So let's talk a little bit about the mechanism. The peroxy acid epoxidation mechanism occurs via a one-step mechanism. This is a concerted process. So don't draw it stepwise, it's concerted. So in this case, first, we have the attack of our alkene on the electron deficient oxygen. We break the oxygen-oxygen bond. We have the attack back onto our alkene. And we have abstraction of a proton in order to regenerate our carboxylic acid. So this is a concerted process where in the end, we have formed our two carbon-oxygen bonds, and we've broken this oxygen-hydrogen bond and formed a new oxygen-hydrogen bond. Really make sure that when you draw mechanisms, if they occur through a concerted process, you draw each of these arrows as one step. Now, what's pretty interesting is that the addition occurs from the least hindered face, resulting in stereoselectivity for certain products. So for example, if there's stereochemical bias in your molecule, you can observe selective epoxidation from the least hindered face. So as we notice, we observe selectivity for epoxidation from the least hindered face. So just like all the previous reactions we looked at, inherent steric bias in your starting material can bias the outcome of this reaction. Okay, so we've seen epoxidation. Now let's talk about why epoxidation is quite useful. From this epoxide intermediate, we can derivatize this epoxide intermediate and modify this epoxide intermediate to yield a range of products. And for epoxide opening, depending on whether your conditions are run under acidic or basic conditions, you get different regioselectivity. So this is really important to keep in mind. We're looking at acid catalyzed epoxide opening now, and it provides us access to transdiol. So epoxide opening under acidic conditions proceeds with Markovnikov selectivity and anti-stereochemistry. Now, if the epoxide opening is performed with an alcohol nucleophile, and I want you to note this and keep this in mind for the exam, or another nucleophile, we can use things other than just water and alcohols. The nucleophile is incorporated at the most substituted position. So this works with a range of nucleophiles, and that's why it's quite useful. So under acidic conditions, we're going to protonate our epoxide. And just like, for example, in bromoetherification, where we are going through a bromonium intermediate, the attack of our nucleophile occurs at the most substituted carbon that can most readily stabilize a positive charge. So if we're comparing a secondary versus a tertiary carbon, which site is preferred for attack? Which site is preferred for attack? Secondary or tertiary? Tertiary, by far, right? Perfect. Okay. So you can best think of this acid catalyzed epoxide opening mechanism as a counterpart to the bromoetherification mechanism that we talked about earlier on in this chapter. Okay, so after we have attack of our alcohol, this attack occurs from the opposite face to our epoxide, and in the end, we end up with a product that has anti-stereochemistry, and the addition occurs with Markovnikov regiochemistry. Now, one thing that I'd like you to appreciate is that if you start with a single epoxide enantiomer, you get a single product. But oftentimes you'll end up with a mixture of epoxides, and as a result, you end up with a mixture of enantiomeric products. So again, this is another stereo-specific reaction. You start with one epoxide stereochemistry, you get out one defined product with the defined stereochemical outcome. Does this reaction make sense to everyone? Does everyone see the parallel to bromoetherification? Okay, perfect. So let's keep going now, and let's talk a little bit about what happens if we're performing epoxide opening under basic conditions. Under basic conditions, we're essentially running an almost SN2-like reaction, where the regiochemistry and the regiochemical selectivity changes pretty dramatically. So, under basic conditions, epoxide opening occurs with anti-Markovnikov regiochemistry and anti-stereochemistry. So in this case, the nucleophile attacks the least hindered carbon. And the beautiful thing about under basic conditions is you can actually get selectivity in terms of which epoxides will react under these conditions. This reaction does not occur efficiently for tertiary carbons. So if you have a highly substituted epoxide, if you react it and try to open the epoxide under basic conditions, you will see selectivity for the least hindered carbon. And as we'll see later on, because this reaction is operating through an SN2-like mechanism, it's very difficult to open a tertiary epoxide. So if you have a highly substituted epoxide and you try to attack it at a tertiary carbon, that reaction occurs so incredibly slowly that it's likely not going to happen efficiently under basic conditions. So does everyone see really clearly here that under basic conditions, we deal with anti-Markovnikov regioselectivity? Does that make sense to everyone? Okay, so if we compare under acidic versus basic conditions, under basic conditions or anionic conditions, we observe selective attack at the least hindered carbon. Under acidic conditions, we observe Markovnikov selectivity, and we observe an attack at the most substituted carbon. So it's really important that you pay attention to the exact conditions used. And the reason why this reaction is so incredibly useful is it accommodates a range of possible nucleophiles. So as long as you have a viable nucleophile, you can substitute and you can open this epoxide with a range of possible nucleophiles, giving you a wide diversity of possible products. Does that idea make sense to everyone? Does everyone see how you can just as easily replace this methanol, or you can just as easily replace methanol or methoxide with like a thiol, like ethane thiol, and this reaction will still just work perfectly fine. Does everyone understand that idea that we can use a range of nucleophiles for this reaction, and this reaction tolerates a range of nucleophiles? Okay, really important idea. Okay, so let's take a look now, and let's look at predicting the products for the following reaction. What type of alkene are we dealing with in this case? What type of alkene are we dealing with? So we see in the chat, we have a lot of students commenting that we have a Z alkene. Perfect, good to know. Really important to know, actually. So again, the reason why we look at a Z and E alkene is if you know the outcome for these sets of Z and E alkenes that we study, the only alkenes that you're ever going to see are Z or E, right? So it provides you a set of generalizable examples. So let me get the model set up, and I'd like you now at this time to put together a model of this structure. You ideally want to be developing the skill to put together and make models of structures you're interested in very quickly, because if you're given a model kit on a more strictly timed exam, you wouldn't want to run out of time just because you're less familiar with making a model of your structure. Okay. So let's talk a little bit about what's the first thing that's going to happen. What is this first reagent? What do we call this first reagent? So it's not quite MCPBA. MCPBA, just for your reference, looks something like this. Metachloroperoxybenzoic acid. Okay. In this case, we have a variant which is peracetic acid. Quite a nasty reagent, but it can also facilitate these epoxidation reactions. And because it's a smaller reagent, it can more efficiently epoxidize hindered positions. What is this first reagent doing? What is this first reagent doing? Would anyone like to comment on that? What is this first reagent going to do to our alkene? What are we going to make after the first step? Just the first step here. What are we going to make? If we treat an alkene with a peroxy acid, what do we get out as our product? So if we treat an so for example, if I took this alkene and I treated it with MCPBA, what would I get out? So if I took this alkene and treated it with MCPBA, what would I get out? see in the chat someone mentioning an alkoxide. Not quite. You don't get an anionic alcohol out. So if in general, when you treat an alkene with a peroxy acid such as MCPBA, what do we get out? What functionality do we end up in our final product? What are we making? It's going back here. So if we treat an alkene with a peroxy acid, what do we get out? An epoxide, right? So let's look and let's study this first step. Let's look and let's study this first step. So in this case, we're treating it with peracetic acid. So this first step occurs through a concerted mechanism, and the epoxide formation occurs with syn stereochemistry. Okay, so let's draw the mechanism out. It's concerted. We have our alkene attacking our electron deficient oxygen. We break our oxygen-oxygen bond, and we abstract our proton. This is a concerted mechanism that occurs with syn stereochemistry. So at the end of this first step, let's now focus on the stereochemistry of our products. So let's unmute our camera and let's look at our alkene. So does everyone see how, let me just make sure everything is, okay. So does everyone see how we have our reactant alkene in this model kit? Does everyone see how this matches our reactant alkene that we're starting with? Okay, now we can either attack from the top or the bottom face. There's no preference in this case. So let's arbitrarily attack from the top face. Inherently in this reaction, you're going to get a mixture of enantiomers because there's no inherent product bias. Oh, sorry, no inherent bias in our starting material. Okay, so we've generated our epoxide. Now, what I want us to focus on is what occurs in terms of our stereochemistry in our product. So looking at the left-hand side, what group is in front? On the left, what group is in front? What group is in front on the left? The methyl, okay. And as a result, what group is in the back on the left? What group is in the back? The ethyl. Okay, what group is in front on the right? Hydrogen, yep. And what group is in back on the right? The methyl, yep. Okay, perfect. So we have our product drawn out. And now in our second step, we're treating it with H3O+. So we have H+ and water floating around. What is our nucleophile going to be? What is our nucleophile going to be? What is our nucleophile? What is going to be adding to our epoxide? What is our nucleophile? Okay, we have someone typing oxygen. What else? What else is part of our nucleophile? You are correct, it's an oxygen-centered nucleophile, but what explicitly is going to be our nucleophile? What's going to be attacking our epoxide? H3O+ is very close. The nucleophile is going to be water. but H3O plus is on the right track. Okay, so now that we've identified our nucleophile, under acid catalyzed conditions, what we're first going to do is we're going to protonate our epoxide. Okay, now our nucleophile is going to attack. And in this case, our nucleophile is water. And what site will water attack? Will it attack the tertiary or secondary site? Which carbon will water attack under acid catalyzed conditions, which prefer Markovnikov selectivity? Which site will water attack? Where will water attack? The most substituted carbon, so the tertiary or the secondary carbon? Most substituted? Tertiary, yep. This attack occurs with Markovnikov selectivity in terms of regiochemistry and anti-Markovnikov stereochemistry. So in turn, that will give us the following product depiction. Okay, and of course we can pull off this proton really quickly. Okay, and once we pull off the proton, we end up with the following anti-diol. Okay, so just to help us visualize what's going on here using our model kit. So we have our epoxide. Water is going to attack at the most hindered carbon with an anti-stereochemistry. So it's going to attack at the following carbon and open our epoxide. So let me show you the product after epoxide opening. So after epoxide opening, we would generate the following anti-product. Okay, notice how both our alcohols are on the opposite face of our molecule. We notice that on the right-hand side, we have our hydrogen and in front and our methyl in back. On the left-hand side, we have our methyl group in front and our ethyl group in back, exactly matching the drawing that we generated. Now, let's do some rotation now and let's draw some equivalent structures. So what I'm going to do now is I'm going to rotate this molecule and we're going to set this molecule up so we have our longest chain clearly visible. Okay, so let's get this set up so the longest chain is clearly visible. So we're just showing different ways that we can rotate our molecule. So if we're drawing this molecule from the following perspective, so we have the longest chain, pretty easy to see. Let's now look from left to right and let's identify what we see. So on the left, what group is pointing towards us? What group is pointing towards us on the left? What is pointing towards us? The alcohol, yep. And what group is pointing away from us? What group is in the back? The methyl, exactly right. Now let's look at the next carbon over. Let's look at our next carbon over. What group is pointing towards us on the next carbon over? The alcohol, yep. And what group is pointing away from us? What group is pointing away from us? So the methyl is drawn in the plane of the page. So if the alcohol is pointing towards us, what group is pointing away from us? The hydrogen. Yeah. Perfect. Now let's do another rotation. And let's just showcase another way of viewing this molecule. So we have our diol. Let's try to view this molecule from the perspective where all of our carbon substituents are drawn. So let's look at our original orientation. Let's look at the original way that we have sort of viewed this molecule. So this is our initial orientation that we viewed this molecule from. Now, what we're going to do is we're going to look at each of our carbon atoms, flat in the plane of the page, and we're just going to draw out what we see for our carbon chain. So in this case, we have our carbon substituents for our 4 main carbons drawn like so. Okay, now let's identify which groups are in the front and in the back. We see in both of these cases which 2 groups are in the front. Which 2 groups are in the front? The alcohols, yep. Okay, and which 2 groups are in the back? Which 2 groups are in the back? Which 2 groups are in the back in this depiction? So if the alcohols are pointing towards us, the ethyl and the hydrogen would be in the back. Exactly right. So on the left-hand side, we have the ethyl group in the back, and we have our hydrogen in the back on the right. So the main reason why we're doing this is to showcase different ways of depicting the same molecule. And as you can see, if you rotate the bonds, you can come up with multiple different depictions for the same structure. Now, of course, you can always check the stereochemistry and just verify that your rotations have not flipped any stereocenters. And I would recommend that you do that when you work through these problems. Does that make sense to everyone? Okay, so let's keep going now and let's look at the next example. This one should be relatively quick because we have a precedent from our E alkene and from our previous studies of E and Z alkenes. So starting off this time, looking at the following structure, what kind of alkene are we dealing with in this case? So we have a Z alkene. Okay. So let's take a look at, and let's try now as an independent example to draw out the products for this reaction. So let's take a moment now and let's try to draw out the products from this reaction with the correct stereochemistry. So let's take about 4 minutes and let's try to use the annotate tool and let's try to predict the products from this reaction with the correct stereochemistry. So let's try to share our responses for the stereochemical outcome of the following reaction using the annotate tool. So don't be shy to share your responses using the annotate tool. And we'll discuss this example in about 3 to 4 minutes. Does anyone have a proposed structure for the product that they'd like to share for this reaction? Does anyone have a proposed structure for the product that they'd like to share? Perfect. And if you have any questions, don't be shy as well to draw the intermediate that you're working through, just so that way it can provide feedback and input on your proposed structures. So let's keep working through these examples and don't be shy to share your proposed structures using the annotate tool, and I'd be happy to provide feedback. This is very similar to the types of problems that you'd be expected to solve on your exam. So it's important that you're familiar with tackling these problems. Okay, this first epoxide intermediate looks reasonable. And let's try to draw the product from the second step, which occurs after epoxide opening. And for the other students who are working through this problem, don't be shy to build on what your other classmates have proposed and drawn out. Um, as I find that elaborating and building off of the work done by the class can often help you connect or fill in any gaps in your reasoning, as well as it allows us to advance this discussion collectively. So the first epoxide intermediate drawn looks reasonable. Of course, we have the other enantiomer as well, but that's okay. This is perfect so far. So let's show what happens after epoxide opening. What does the product look like? And you don't have to draw all three different ways of drawing the product. Just one would be enough for now. And don't be shy to contribute the proposed structure of the product using the annotate tool. You could also draw out the mechanistic steps that get us from each of our reactants to the first and second product. Let's keep working on this example. I'd like to see that the class is able to work through an example like this. And if there are any questions that arise as you work through this example, don't be shy to let me know. So we have our proposed product being drawn out by one of our students. So we have a proposed product for the second epoxide opening step, and I have a question based on this. So does epoxide opening occur with cis or trans selectivity? Or let me phrase it another way. Does epoxide opening occur anti or syn? So when we open up our epoxide, and we think about the two possible faces that water can attack from, which face is water going to prefer to attack from? The same face as the epoxide or the opposite face? What does the class think? So when we talked about our epoxide opening mechanism, Does epoxide opening in this previous example that we looked at, does it occur from the same face as our epoxide or the opposite face? Opposite, right? So then looking at this mechanism, looking at the product that you've drawn, did your attack as drawn came from the same face when we know that epoxide opening occurs from the opposite face to our epoxide? Would you like to revise your product to account for this? And for the other members of the class, don't be shy to chime in, drawing your own proposed structure as well. Would you be able to revise this structure in light of this mechanism? Let me take a look. That is fine, but that's a bit of an odd way of drawing this structure, but that is a reasonable answer. Yeah. Let's now take a look at this problem together. Let's now take a look at this problem together and let's talk through what's going on. Yeah, that response was perfectly fine. So let's look at this example together and let's try to predict the stereochemical outcome of this reaction, and let's draw out our product. Okay, so let's start first and foremost with a model. So here is our alkene. So when we have our peroxy acid, the peroxy acid will react with our alkene. And the addition and our epoxidation occurs with syn selectivity. So our epoxide can either add from the top or the bottom face. We're arbitrarily going to choose the top face. And the epoxide was drawn perfectly. There were no issues with the epoxide drawn. So we generate our epoxide, and what groups are in front? What groups are in front? So in our epoxide, what groups are in front? The methyls, right? Okay, now in the presence of H3O+, we can protonate our epoxide. And once we do that, we've now activated our epoxide for further reaction. Okay, now this is the really important part. Water, if we look at these two carbons, both of these carbons are secondary. So is there any preference in terms of where water attacks? Is there any preference? Are both of these sites viable? Can we attack it either? Yeah. So let's attack on the left. Let's arbitrarily choose to attack on the left and open up our epoxide. So we're attacking on the left and we're opening up our epoxide. This attack occurs from the opposite face to our epoxide, and as a result, our alcohols end up anti or trans to each other. So we have our alcohol on the right pointing up and our alcohol on the left pointing down. So just draw them without any dash or wedge, one up, one down. Does that make sense? So the way that you drew the product was fine. It's just you drew the product and then you rotated it. So it took me a moment to figure out what was drawn. Not that it's not perfectly viable, but I find if you go through this standardized step-by-step method, it can save you some accidental issues where you rotate the molecule and somehow end up flipping substituents. Okay, so in terms of our product, what groups are pointing towards us on the left? What's pointing towards us on the left? The methyl. Yep, so we draw the methyl and our hydrogen's pointing away from us. On the right, what group is pointing towards us? What group is pointing towards us on the right? The methyl. And hydrogen's pointing away from us. Now, just to show for completeness sake, we just need to deprotonate our alcohol and get our final product out. So let's do just that. So in terms of our final product, we have the following. We have the following diol as our final product. Now, we can also rotate this product. We can also rotate this molecule so that, one, we're just looking at our chain as normal. So we can rotate this molecule. So we're looking at a typical straight chain alkene. So let's draw out our straight chain. And let's look now. So starting off on the left. So starting off on the left, looking at this structure, on the left, what group is pointing towards us currently? What group is pointing towards us? The hydrogen, yep. So we draw the hydrogen and then our alcohol is pointing away from us. Okay, on the right, what group is pointing towards us? On the right, what group is pointing towards us? The hydrogen once again. And the alcohol is pointing away from us. So these are two ways of viewing this structure. The only thing that we've done is just subjected this molecule to rotation. Heck, even if you wanted, you could potentially rotate this molecule one more time and end up with the following depiction. There are many ways of drawing. Your molecules based on how you rotate your structure. So it's really important that you take things one step at a time and that each of your rotation steps, you make sure that you're keeping the relative arrangement of your bonds the same. Does that make sense to everyone? Okay, so let's keep going now. And let's look at some other examples. So what we're next going to look at is syn dihydroxylation. So epoxide opening gives us anti-products. In the case of osmium facilitated dihydroxylation, we get syn dihydroxylation, where both of our alcohols are installed on the same face. So syn dihydroxylation is facilitated with osmium tetraoxide with sodium bisulfite used to cleave off our osmate ester. This occurs via cyclic osmate diester intermediate, and the sodium bisulfite is breaking and helping facilitate dissociation of this osmium catalyst from our diol. So this is a reducing agent that's designed to help break this osmium oxygen bond and free out our alcohol. If you just stopped at this first step, you'd actually isolate the osmate ester, and it's pretty hard to get this osmium off without reducing it off or using pretty strongly basic hydrolyzing conditions. Now, you can also do the same syn dihydroxylation with potassium permanganate. But you have to be careful because permanganate can cleave diols to yield carbonyls. Okay. So let's do some product prediction. So in this case, we're asked to predict the products of the following reaction and provide a mechanism. So in this case, we're looking at an E-alkene. Okay. So in this mechanism, osmium tetraoxide is going to associate to our alkene. Now, just as a question, just looking at how these arrows are drawn, is osmium functioning as an oxidizing or reducing agent? What is osmium doing to our alkene? Is our alkene being oxidized in this process? Yes. Right. You see osmium is picking up some electron density from our alkene. Okay. So we then make the osmate ester. That's what you get out of step 1, the osmate ester. Now, since this addition occurs with syn stereochemistry, our diol will end up on the same face. Okay? Does everyone notice how both of our alcohols are on the same face? So to help us visualize what's happening, let's start with our alkene. So we have our typical trans alkene, right? We have our typical E-alkene, and our diols are going to be installed on the same face. Okay. So let's install both of the diols on the same face. Okay, so we have both of our diols installed on the same face. Okay, so let's redraw this to match what we're doing with our model kit. Let's just redraw this to match what we're doing with our model kit, just so that way everything is consistent. Okay, so we have both of our alcohols on the bottom face. Now, let's look at what groups are in the front and in the back. So, starting off on the right, which group is in the front on the right? On the right? The hydrogen, yeah. The methyl's in the back on the right. Okay, what about on the left? The methyl. Okay, perfect. I always try to switch up the order that I ask that question just to make sure that the responses are actually, yeah, no problem. It's always important just to check to make sure. It's okay, no worries. Okay, so now that we have the osmate ester, after treatment with sodium hydrogen sulfite and water, essentially what ends up happening is we end up hydrolyzing our osmate ester. You don't have to know the mechanism for this second step, since depending on the exact reagents used, the hydrolysis functions slightly differently. The main thing that we're interested in is that after this reductive cleavage or hydrolysis, we end up freeing out our diol. Now, what I want us to look at is how we can rotate this structure to model all the different ways that we can draw this structure. So if we wanted to rotate this molecule, this diol is directly equivalent to the following diol. Now let's look at our stereochemistries. So on the right, which group is in front? On the right, the hydrogen's still in front. We haven't done any rotation on the right. Okay, and now on the left, which group is in front? On the left, which group? Hydrogen, yep. Okay, let's do one more rotation. Let's look at our alkene as if it were a normal straight chain alkene, like so. So let's draw our typical zigzag pattern for the straight chain alkene. And now which group is in front on the left? Which group is in front on the left? Hydrogen, right? Okay, and which group is in front on the right? Which group is in front on the right? Hydrogen, yep. So these are all the different ways of depicting this structure. Does this make sense to everyone? Does everyone notice the distinction between dihydroxylation and epoxidation? Does everyone see the distinction in terms of stereochemical outcome? Dihydroxylation leads to a syn-diol. Epoxidation and opening leads to an anti-diol or trans-diol. Does that idea make sense to everyone? Does that idea make sense? Okay, so to finish off this section, what we're now going to look at is the reaction of a Z alkene under dihydroxylation conditions. So just like before, we have our alkene and our osmium adds in a syn manner to our alkene. And that in turn gives us the osmate ester. And now looking at the stereochemical outcome, for this process. So we have our Z alkene. We can arbitrarily choose to add from the top or the bottom face. We're going to add arbitrarily from the bottom face. Okay, so here's our diol, right? So after treatment with sodium hydrogen sulfite and water, we cleave off our osmate ester. And we're left with our diol. Now, let's take a look at the stereochemistry. What groups are in front in this molecule? What groups are in front? What groups are in front in this diol as drawn from our model? Hydrogen, yep. And what groups are in the back? The methyls, yep. There we go. Now, of course, we can rotate this structure. And now as drawn, if we rotate this structure, we still have our hydrogen in front and methylene back on the right. But on the left, what group do we now have in front on the left? What group is in front now on the left after rotation? The methyl. And now, just for completeness sake, let's look at our typical straight chain alkene. And we already see that because we adjusted our alkene stereochemistry, we notice that we flipped one of our stereocenters. So now on the left, what is in front after rotation? On the left, what is in front? The alcohol. Yep. Well, on the right, the hydrogen still in front. Perfect. Does everyone notice how changing your alkene stereochemistry and geometry directly changes the stereochemistry of your product? Does that idea make sense to everyone? Perfect. Perfect. Okay, so in terms of, this is a good stopping point for today. We're likely going to finish this chapter next class session next week. And then likely what we're going to do is we're going to move on to the chapter 10 note set. And then once we finish chapter 10, we'll go to chapter 8. The reason why we're moving slightly out of order is that chapter 10 is thematically related to concepts covered in this chapter on alkene addition and modification. And chapter 10 is a very important chapter to really tie together all of these concepts and really show how once we've generated these products with defined stereochemistry, what tools do we have to modify each stereocenter and what tools do we have in order to generate alkenes with defined regioselectivity and generate stereocenters with defined stereochemical outcomes. Okay, so with that said,